Hi, I'm Josh,
Hi, I'm Draven.
and we're going to present section 12.2. We're going to start with a version of Fermat's last theorem. So Fermat's last theorem says that x to the n plus y to the n equals z to the n has no solutions for n greater than 2. So Fermat said that he had a ingenious proof of it in a note to one of his colleagues, but we have no actual proof that he proved it for all n. But we do have a proof from him that he figured out for n equals 4. So we're gonna look through that. Although we're gonna prove a slightly different version. We're gonna change the z to the fourth to z squared. It's a little bit of a stronger statement, and so theorem 12.3 is Fermat's last theorem specifically for n equals 4, but using z squared instead of z to the fourth. So Fermat's proof uses something called infinite descent. The idea is going to be that we're going to assume that there's a solution, and then we're going to find a second solution that's smaller than that, that's less than the original solution. And then we'll be able to do it again and again and again, and in an infinite way, although there aren't an infinite number of integers less than a given value. Eventually we hit 0. So that's where we'll hit our contradiction. So working toward a contradiction, we'll assume that there exists a solution. We'll call it x naught, y naught, z naught. We'll further assume that the greatest common denominator of x and y is going to be 1. And the reason that we can do this is because if we assume that it has some other common denominator, then we can just sort of visualize what happens. This would, x naught would become dx1, y naught would be dy1, etc. And then we could divide all that out, and we'd end up with another x1 to the fourth plus y1 to the fourth equals z1 squared, where it would have the greatest common denominator of 1. So we can assume that the GCD of x naught and y naught is 1 without any damage. So we write the equation this way, and then we can rewrite it slightly so that the x to the fourths and y to the fourths become x naught squared squared and y naught squared squared. And now we have a primitive Pythagorean triple. So this hopefully sounds familiar from 12.1. And based on that, we have some properties that we know of, and we can apply theorem 12.1. One of the things that theorem 12.1 says is that one of x and y has to be even. So we'll assume that it's x naught squared that's even. And so based on that, using theorem 12.1, we come up with this: x naught squared equals 2st, y naught squared equals s squared minus t squared, and z naught is s squared plus t squared. So again, recall from section 12.1 that only one of s and t is going to be an even number. So we'll assume for a moment that s is the even number, and we'll recall this little gem from many chapters ago, that any square integer has to be of the form 4k or 4k plus 1. And so if x naught is the even one, then y naught squared would be the odd integer, so it must be congruent to 1 mod 4. So y naught squared from the previous slide is s squared minus t squared mod 4. So again, we've assumed that s is even, so s would be congruent to 0 mod 4. We're assuming that t is odd, so it would be congruent to 1 mod 4. And so finally we end up with 3 mod 4, but that's a contradiction. One isn't congruent to 3 mod 4. So what that tells us is s must be the odd one and t must be the even one. So there exists some r such that t equals 2r. All right, I'm going to hand it over to Draven where she can finish up the second half of this proof.
Okay, so we just learned that due to our contradiction, there exists an r such that t equals 2r. So now we're going to write our x naught squared as 2st. We're going to write that as, it's now going to become x naught squared as 4sr, or alternately as x naught divided by 2 quantity squared equals sr. Then by lemma 2 from 12.1, we know that both s and r have to be perfect squares. So from that, we can let S be Z sub 1 squared, and we can let R be W sub 1 squared. And from there, we can derive the equation T squared plus Y naught squared equals S squared. And this is going to be another primitive Pythagorean triple. And from here, we're going to note that T is still even. So we're going to use 12.1 again to say that T is going to be equal to 2UV, and Y naught is going to be equal to U squared minus V squared, and S is going to be equal to U squared plus V squared, and U and V are going to be relatively prime. And then from there, we're going to use lemma 2 again to say that both U and V are squares, and we're going to let them denote them as U as equal to X sub 1 squared and V as Y sub 1 squared. And then we're going to substitute those into the equation above to get the following equation. And then from there, we've got a second solution with an important characteristic as shown. And we can repeat this argument again to get a third one, and then a fourth, and so on and so forth. And eventually we're just going to run out of positive integers, which is going to be a contradiction, which therefore leads us to our conclusion that there are no positive integer solutions to the equation x to the fourth plus y to the fourth equals z squared. So from theorem 12.3, we get an additional corollary that says the equation x to the fourth plus y to the fourth equals z to the fourth has no solutions in the positive integers, which is the original equation we were talking about before we got started. So there's a lot of history that goes into Euler's last theorem. A lot of people have been trying to solve it. Euler gave the first proof following Fermat's proof of n equals 4 for the prime p equals 3 in 1770, but he left some things out. And Lagrange, is that how you say it? Supported the proof later on and supplied the missing statements. And then Lagrange and Dirichlet each proved the case of p equals 5 and 18, 25 by themselves. And then we've got Kummer and Faltings and several other mathematicians are also, they're contributing to the expansion of the proof to the point where we get it true to the exponents up to 4 million by 1992, which is quite a lot. And then in 1993, Andrew Wiles makes one last big breakthrough. However, his first proof was wrong. There was quite a bit of errors in it. It is 200 pages long, and after he got done, he had errors in it, and when he revised it, made it shorter, and it was actually widely accepted and is still accepted today. So going along with that, we also have the Diophantine equation, x to the fourth minus y to the fourth equals z squared. And we're going to say that that has no solution in positive integers x, y, or z. This also comes from Fermat's last theorem. It's also proved using a contradiction.
All right, so I'm going to jump back in and talk about theorem 12.5. 12.5 basically says that if you have a Pythagorean triangle, which I think was defined in 12.1 as well, that the area of that triangle can never be a perfect integer square. So the proof for that comes from looking at the standard formula for the area of a triangle that we all learned in high school. So let's suppose that this area is a perfect square, and we'll just call it u squared. Then that would lead us to this, 2xy equals 4u squared. And from that, we're going to both add and subtract the regular Pythagorean theorem equation. So that would be taking 2xy plus 4u squared and adding x squared plus y squared and on the left and z squared on the right. And then we'll also subtract that, or we'll subtract this 2xy equals 4u squared from the Pythagorean theorem is what I should say. And we can see the result here at the top. And if we multiply those two equations together, we get what amounts to, in this line, x squared minus y squared squared equals z to the fourth minus 2u to the fourth. So from theorem 12.4, which we mentioned just a minute ago, we have a difference of 2/4 powers that equals a square, which we know has no solution. So therefore, we can't have a Pythagorean triangle whose area is a square. So there are quite a few problems that still exist in this realm. One of them is that, are there an infinite number of Pythagorean triangles whose sides are one less than a perfect square? Interesting. I thought this was interesting since we started the year off talking about triangular numbers. Is, are there an infinite number of Pythagorean triangles whose sides are triangular numbers? There are a couple of examples listed in the book, but it's as of yet unproven whether or not they're an infinite number. And then there's the Catalan equation, and it takes several forms. There have been some proofs for it for certain values of m or n, but no general proof exists overall about whether or not there are any solutions to the Catalan equation in general.
We're going to work one last problem from the homework section. It's kind of an application. And it's homework problem number 3. And the question says, or the statement is, in a Pythagorean triple, x, y, and z, prove that not more than one of x, y, or z can be a perfect square. So we're going to prove this by way of contradiction. And this actually requires 2 cases. So in case 1, we're going to assume that both x and y are perfect squares. So we're going to let x be a squared and y be b squared for some a and b. So we know that since they're a Pythagorean triple, the statement x squared plus y squared plus z squared is going to be true. So then by substitution and the fact that x equals a squared and y equals b squared, we get the following statement that a squared squared plus b squared squared is equal to z squared. We can simplify that to a to the fourth plus b to the fourth equals z squared. And we're going to claim that that has a solution from what we've just done with substitution. However, the theorem we just proved with 12.3 says that that equation has no solution, and therefore we have a contradiction saying, so we know that that can't be true. Our case 2, we're going to let our perfect squares be on either side of the equation. So we're going to let, without loss of generality, we're going to let x be a squared and z be b squared for some a and b. And again, we know that x squared plus y squared equals z squared. But this time we're going to rearrange it and get x and z on the same side. And then by substitution, we're going to get the following equation. And we can reduce it to get a to the fourth minus b to the fourth equals y squared. And that also has a solution, but then by theorem 12.4, which we mentioned earlier in the presentation, we know that the above equation cannot have a solution, and therefore we have a contradiction for both cases, proving that not more than one of a Pythagorean triple can be a perfect square.